you have the idea now for what we're doing. Basically, we're testing for differences in different things. And those different things can be a lot of different things. And I know this is super unspecific, but it really can. We can, and you'll see the wide range of things we can be looking at. We will go through these different kinds of tests and calculations. The 2-sample test for paired data, 2-sample test for independent group data, statistical power and sample size, comparing many means with ANOVA, and the multiple testing problem, and then we will do some examples. Okay. We can compare our basically 2 different population means. Remember how when we were testing last chapter, we were looking at basically is it likely that this sample came from this population, or is there an alternate population that this sample came from? And there are actually a couple ways you can do that. You can do paired measurements where each observation is logically matched to another observation. And you can do, and that would be like you take a standardized test, you take the ACT, and then you take a prep test or a prep course, and then take the ACT again. Well, hopefully you do better the second time. And it would be useful to know whether or not you really did better, or, if, it could have been random. You're just in the margin of error there. Okay. You can also have 2 independent sets of measurements where the observations can't be matched on a one-to-one basis. Now, this I think would be to me would be a more convincing study, because you'd have scores on standardized tests of students who did not take the prep course versus those who did. And the reason that actually is more convincing to me is because, well, you guys took the ACT, right? And the experience of taking the ACT or those tests is part of the training progress or process for taking those tests. Because most people do much worse on the first time than they do later. I mean, if you happen to be a genius and knock it out of the park on try 1, then awesome. Come take my test for me. But most of us need the experience of sitting in the room for 4 hours, and I don't know, is it even on paper anymore for you guys? Okay. Number 2 pencil making circles in there. Those 4 hours, that's a meaningful experience that changes the way you take the exam, and the fatigue that comes with it. Like if you guys go to grad school or want to go to grad school, so you take the GRE or the LSAT if you want to go to law school. I don't know anything about the MCAT if you want to go to med school. Fatigue is like a major part of the exam process, because it's like, I think the LSAT was 4 hours as well, and the GRE was 6, I think. I mean, it was brutal, and taking it again would be helpful. I only took it once. That was a dumb move. Anyway, that would be a more convincing test to me. But in any case, the nature of the data dictates which 2-sample testing procedure is appropriate, whether you have paired or independent group data. Paired data. So here's a question that you could ask yourself. Did a new wetsuit design allow for increased swim velocities during the 2000 Olympics? I think that was when the men were wearing like the trunks to a suit thing. And apparently the swimsuit was slicker than your skin. So it was, I think they made it, I think that's why the men aren't allowed to wear anything but the things supposedly. Anyway, how would you want to measure that? Because you could randomly choose, if you're just going to grab swimmers, maybe you grab the wrong ones. Maybe you grab Michael Phelps and put him in the suit and everybody else in something else. Well, of course, you've screwed up the study at that point. The dude swims fast, or did. Maybe it would be better if you had him swim once with the suit and then maybe later, after some rest, with a different suit. And then you have somebody else swim again or swim in a different order. And you have these orders mixed or something like that. What you could do is you could measure the velocity for each trial and the velocity difference. So you might end up with a data set that looks something like this. You got swimmer numbers 1 through 12, and this wetsuit velocity of 1.57 and this swimsuit velocity of 1.49. I have no idea which is which, but let's just play along that one of them is a swimsuit that people think is good and the other one's not. And then you can find the velocity difference right here. Now the question at hand is, you want to know if that suit makes a difference. Like, should this, the Olympic Committee would be asking, should this suit be allowed? Or do we want to have rules that prevent you from doing that? So they would want to know if this number here is different than 0. Okay, well, that's interesting. How do you find that? Well, the velocities are paired by swimmer. So each swimmer has 2 velocity movements or velocity measurements. And suppose that each swimmer we have observations XIWS and XISS. So XIWS wetsuit, XISS is the swimsuit. Then we let DI be the difference between the 2 measurements. So DI is equal to XI minus WS, or XIWS and minus XISS right here. So based on the difference, the sample mean of the DI is D bar. Basically, all we've done is, instead of using X's all the time, now we're using a D for difference. That's all we're interested in right now. Now, we can suppose that they're in the population of swimmers. We want to know if there's a difference in this happening because we're sampling. So we're going to let delta, lowercase d, lowercase delta, it's the squiggle. If you don't know your lowercase Greek alphabet, there. So let delta be the population mean of the difference in velocities during a 1,500 meter swim if all competitive swimmers recorded swim velocities with each suit type. So suppose you had everyone who swims competitively do this test, then our null hypothesis would be that H naught is the delta is equal to 0. So there's no difference between wearing these 2 suits. Okay, so that would be our null. Our alternative is that there is a difference. So delta not equal to 0. I guess presumably it could be worse, it could be better. We just want to know if it's different. Okay, so the formula for this test statistic, we're going to use a T because we've sampled, and it's just like what we used in the last unit. So D bar minus delta naught over standard deviation divided by square root n. So D bar is the mean of differences, SD is the standard deviation of the differences, and n is the number of differences, so the number of pairs. Essentially, it's a one sample test of difference values. The p-value, if we wanted to calculate, is the same from a t distribution of df equals n minus 1. Okay, so this feels familiar, right? I mean, you've seen it. You may not feel super comfortable with it, but you've seen it. You've done a few of them. And it's basically the same thing, only that we're just looking at differences now instead of them being that whether or not the means are the same. So let's see here. So our confidence interval formula is the same. Basically, that we're looking for a confidence interval of the mean difference. So d bar plus or minus t star times the standard deviation of differences divided by square root of n. And where t star is the point on t distribution with df equals n minus 1 and has the area 0.025 to its right. So, it's just, and that's why I was doing so the 0.25 to its right, that means it's 5% on both sides, both tails. Okay. For this part of I know you guys aren't using R, but we're just the software. So we will do examples. But for right now, we're just kind of gonna walk through the software results so that you get the intuition without having to go through the calculation. I don't know if this is the best thing in the world or not, but it's worth a try. Okay, so if you do conduct this t-test with the formula that you have there, you end up with a t of 12.318 and degrees of freedom of 11 and p-value of really freaking small, scientifically speaking, because there's 7 zeros on this side of on that 8. Okay. I'm thinking that we reject the null on this one. What do you think? So the null was that there was no difference. Now we've got a really large t-value and we have a p-value that is really small. So it seems to me like there's a difference between these suits. You agree? Yeah. Okay. So that is now of course we could do this. You could do this differently. But let's say what you have, well, to come up with a different example, we need a different set of data. And this is a non-dominant arm strength after resistance training data set. If you've read the chapters, you've seen this data set before, but basically it's got the individual here, their sex, their age, race, height, weight, and then some measurements of strength. So what we're looking for here is is there a difference between non-dominant arm strength after whatever that was by sex? So, looking at this, that looks like there might be a difference. I mean, this is a lot higher. I'm a little concerned that the medians overlap a little bit though. So just by visual, I would be, it may not be, but this is why you do tests, so that you don't have to rely on your eyes. But you understand why you might want to know the difference between response to this training by sex. Or is there a difference between male and female response to this training? Maybe you shouldn't. Maybe you need the target for what you're doing. So your null hypothesis would be that if we were to do this training with everyone, then the population mean change in arm strength for women would be the same as the population mean change in arm strength for men. So not that they have the same strength, but that they grow at this, or that their strength changes at the same rate, basically. with response to this training. Your alternative hypothesis is they're not. They're not the same. Our parameter of interest is basically mu1 minus mu2. So is there a difference between these two means? And our point estimate is the sample means. So we have our population parameter and our sample estimate here. Yes, as an aside here, it's saying that in general we use mu1 or x1, mu2. Don't do that unless you want to get confused. Like even when you're doing stuff by hand, it's better if you go ahead and use some sort of subscript that means something to yourself. That way you don't get confused. The t statistic that we're going to use now is this right here. So it's x bar minus 1, x bar 1 minus x bar 2 minus mu1 minus mu2 all over the square root of the standard deviation of 1 squared. So it'd be the variance divided by n, and the standard deviation squared. So the variance divided by n2. P-value is basically the same, but we're not messing with that as much since we live in a world of doing stuff by hand. We'll do some examples of that, of what you can do by hand. But like I said, we're more concerned about failing or rejecting or failing to reject a hypothesis in the back of the book than the p-value in this class. The degrees of freedom is a bit different than what you're used to dealing with. So the degrees of freedom is equal to the minimum of n minus 1 or n1 minus 1 and n2 minus 2. So if your men's group had 15 people and your women's group had 14 people, then one of those would be 15 minus 1, one of them would be 14 minus 1. So your degrees of freedom would be 13 by that estimation. Does that make sense? Okay. In R, it uses this crazy thing, and it comes up with a different number. Obviously, that's not what you're doing. Just for clarity, you guys don't have to do this. Just know that there are approximation issues because we're dealing with a sample here. Our 95% confidence interval for the difference in population means has the form of x bar 1 minus x bar 2, so the difference in means, plus or minus t star times variance in 1 plus variance in 2. Okay, and again, it's the same. It's the same to the right, same critical value. Okay. If we let the software do the work, we saw the differences graphed there. It looks like there is a difference. That's a pretty big t-score, and that's a very large p-value or a very small p-value. I would say that we can reject the null and say that there is a difference in response to this training between men and women. Now, what if we switch back to the swimsuit data? And if we had, remember how that had a huge p-value or a huge t-score or t-value and a really tiny p-value? So we rejected the null. So say we had independently or incorrectly analyzed that as an independent two-group test. So it was in ignoring the fact that the swimmers were linked between the groups. If we did that, we would end up with a t of 1.368 and a p-value of 0.1849. So we would fail to reject the null in that case. So that kind of illustrates the importance of understanding what you're studying and making sure that you choose the right test. Because if you could choose the wrong test and end up with the wrong answer. That's what I'm trying to say. Okay. Here we have an example. So I helped some students with a test, with a feed trial, where we had two groups of calves. I'm trying really hard to say calves instead of kevs, so that you all understand what I'm saying. One group was on pearl millet, and the other group was on pearl millet plus soybeans. You're thinking, man, cool, you give them more feed, probably a good thing. I don't know. They didn't tell me whether or not it'd be a good thing. They just told me they wanted to know the difference between the two, or if there was a difference. And if you're looking at this graph, might be thinking, yeah, B is higher, isn't it? But you also might notice that a lot of these animals started heavier. And we're not really interested in whether or not the end or beginning and ending weight. We're interested in how much weight they put on over the course of the trial. How much weight do they gain over the trial? So the absolute weight really isn't all that useful to us, is it? I mean, it's a nice illustration for what we're going to look at, but what we really are interested in is the differences. So our two sample test would be, because we can't run the same animal through the test twice. They're only however many days old once. If we could repeat life multiple times and have, you go to the doctor and he says, is this medicine working? And you're saying, I don't know, I only get to live life once. I don't have a counter to know if it's working or not. Counter example. We don't get to do that with this. So with this feeding of animals. So we basically have to have two different samples. So when we want to know if we were to feed animals just the pearl millet, and if we were to feed the animals just the soybeans and the pearl millet, are they different? So our null hypothesis is that they're not different. This should be not equal. So we can do this by hand, and I was pulling what little hair I have left out over this morning, because I was doing this. I found my standard deviation for this, and my n is here, and here's the difference. Here's the means for the two different groups. And we want to know if the hypothesized mean is different from 0. So, we don't actually need to have this right here. We can just have, we can leave it off entirely, because minus 0 is 0. But you could conceivably have a hypothesized difference where you think that something, for a reason, is going to be, for some reason you think that there's a 5 pound per day difference or something crazy, or maybe not crazy. Anyway, a non-zero difference, you have a reason to believe that that's the case. And then you could test and see if that is the case, or if it's different from that non-zero difference. These values right here are the standard deviation, not the variance. So I didn't square those like this formula says you need to. And I ended up with a t is equal to 5.52. And I had run the software and I found out that the t was equal to 0.7952. So I could have used a prettier graph. I have a pretty graph, colors, rejection zones, and everything. It was amazing, but I did that anyway. Okay. So what I guess I'm showing my humanness here, and I don't like that. But in any case, at t of equal to 0.7952, it charts to around, or it would plot to around here if I was graphing the t's. You could look it up in a table to see that it's not anywhere near significant. So we would fail to reject. I guess we can take comfort in the fact that I did it right when it meant something, and just failed to do it right by hand for y'all. Anyway, here's the fail to reject. So in this case, there was no difference between the feed rations. Now, just as an aside, they think that the two girls running the study think that there might be a difference later on. The animals might be gaining better now that we're on that track. But I mean, that wasn't the study. The study was 90 days, average daily gain between these two treatments. Is there any difference? And no. It's a real bummer. Nobody likes to present that. Okay. You've probably heard these terms, and they've probably been used maybe wrong. But most studies are done to establish evidence in favor of an alternative hypothesis. So that's why we were disappointed when we didn't find a difference. It's not that we were rooting for soybeans, like, yo, soybeans are great. It was that, we do this stuff because we're like, I wonder if there's a difference. And then you find out that there isn't one, and you're like, yeah, it's kind of boring after all. So I guess it sounds unscientific, probably, but if you didn't think there was a difference, you wouldn't do it. So that's the fact. Most of these studies are done to establish evidence in favor of an alternative hypothesis. And so we need to figure out a way of quantifying our probability that we do it right, that we reject it when we should. So the power of a statistical test is the probability that the test will reject the null hypothesis when the alternative hypothesis is true. So this is you are trying someone who turns out to be a murderer, and the jury convicts them. So they have rejected the null hypothesis that you are innocent until proven guilty, and they said, guilty. And this is the probability of them getting that right. So the power depends on the hypothesized difference between two population means, also known as the effect size. So mu1 minus mu2, the absolute value of it. It matters, the standard deviations matter, and the sample sizes matter. And usually you're only you can only control the sample size. So what we do is we can use some formulas to determine whether or not you have a big enough sample size to have a high enough power of the test that's worthwhile. Now, I want to remind you and myself that these outcomes, these errors in testing. So type 1 error is when you reject H naught, but H naught is true. So that's a type 1 error, and it's a false positive. This would be convicting an innocent person. That's bad. I don't want to convict a bad, right? I mean, that's bad. Okay, so you fail to reject H naught, and H naught is true. Okay, well, that's the good one. That means that you have failed to convict an innocent person. So that's good. I like that one. Or you could have another no error scenario where you reject H naught and HA is true. So you convicted a murderer. So it's a good thing, or you're a guilty person. But you can also have a type 2 error where the probability is beta, where you're false negative. So you fail to reject H naught, and the alternative hypothesis is true. So this is letting a guilty person go free. And it's just like, well, no, not just like the criminal justice system. The criminal justice system, you're supposed to, beyond a reasonable doubt, you're supposed to have no doubt. Maybe this would be more like civil cases. Civil cases are the preponderance of evidence. So basically, like, if you're in a jury and you think, oh, it's a 51% chance that this guy's responsible, then yeah, good. But it's 100% in the criminal justice system. It's supposed to be. So in science, what we try to do is balance the probability of, and balance it. I don't mean we take a 50-50 shot at it. I mean that we severely really don't want to fall. We really don't want to accidentally we don't want to have a type 1 error, basically, because we look at that as being the worst possible outcome here, where we say that there's a difference when there's not. That's the worst one. So we want to minimize, well, we don't want to minimize this. We could minimize it to 0. We're going to choose a value of alpha. Remember, alpha is our level of significance that we're willing to accept the probability of getting that wrong. So that's going to be 1%, 5%, 10%, something like that, but it shouldn't be any more than that. And beta is our opposite. It's the probability of type 2 error. Okay. Type 1 error is controlled by rejecting H naught when p-value is smaller than alpha. That's it. That's how we do that. Type 2 error and power is affected by sample size, standard deviation, and effect size. As sample size increases, the power increases. As standard deviation decreases, the power decreases. And as the effect size increases, power increases. And our study design often includes calculating a study size or a sample size that so that the probability of rejecting a null hypothesis is acceptably large. So we might want to have a probability of assuming that that's the right thing to do, of 80 to 90%. So it's important to have a precise sample size. It needs to be large enough to allow for sufficient power to detect a difference between groups. So maybe those 15 animals each, maybe there just wasn't enough of them. I actually didn't test for this, I don't know. Maybe there was a difference, but we were unable to detect it based off of the fact that we had too small of a sample. Possible, isn't it? Making me want to go back to my office and test for that. Anyway, however, unnecessarily large studies are expensive and can be unethical. Now, how on earth would a large study be unethical? Other than wasting money and resources. Yeah. See, yes, I really had to sit around for a while and think about this. This is why I'm making you think about it too. So think about it in terms of a human trial. You ever wonder, well, actually, I don't think that's how they do that. You have sick people who have a disease, and you give some of them a placebo and some of them a drug that could fix it. Okay, so the people that get the placebo aren't getting the thing that'll fix it. I don't know about you, but I would not want to be that dude. I would rather personally have the untested thing that we think is going to work, because something's wrong with me. I don't know enough about human medical trials, but I always find myself wondering. They say whenever they're doing research on an AIDS vaccine or HIV vaccine, where do you find volunteers for that trial? Think about that. We're going to give you a vaccine that could be a placebo. Go on and live your life. We're going to give you a vaccine that's real. Go on and live your life. No thanks. But maybe there's more to that than I know about. I'm guessing there is. I know one thing. I'm not volunteering. Wouldn't be a very interesting trial anyway, though, because I'm married and all. But anyway, anyway, it took me a while to come up with a reason that might be unethical, and I think that's it. That's what I'm coming up with. Either you're denying people the thing that could be fixing them, or you could actually be doing something dangerous to them. Maybe the thing you want to do, the drug you want to give these people actually turns out to be deadly. It happens. Or dangerous. It happens to be worth it or the side effects happen to be worth it for considering the alternative. So like the side effects for, HIV PrEP, if you know anything about that, that's a pill you can take to not get HIV. The side effects on that are wicked. Yeah. If you go to Africa, you might want to know. But the side effects are wicked. So you wouldn't want to expose more people to the side effects than you have to. Anyway, unethical. Who'd have thought? So how do we calculate a big enough sample size? We need some information. In this formula here, we can calculate the difference here by using mu1 and mu2 and sigma 1 and sigma 2 for the population means and standard deviations of the two groups. We might have to approximate those or come up with something for that. The difference is the minimally important difference that investigators wish to detect. So this delta here. So that would be, you want to detect a certain amount of difference between, back to the feed trial, how much average daily gain would be meaningful to have noticed? I honestly don't know. But that's what you would want to do. You want to figure out how much of that would be meaningful, and then we would plug that in there. The null and alternative hypotheses are that delta is equal to 0, so there's no difference between the means, and the alternative that delta is not equal to 0, there's a two-sided alternative. I also don't have a reason why we switched from lowercase delta to uppercase delta. I don't have a reason for that. Sorry. The two-sided significance level is alpha. So our z-score, so in this case, we're using a z because this was from an example where we have sufficient numbers to be sampling from the normal distribution rather than a t. So our two-sided level of alpha, so with the area on left and right. So alpha divided by 2 on left and alpha divided by 2 on the right. Our beta is the probability of incorrectly failing to reject H naught for a specified value of delta. So 1 minus beta is the power, and the value z minus z, 1 minus beta is the point on the standard normal distribution with 1 minus beta to its left. We have an example, don't worry. Once you have that, you can calculate the power of the test through this. We'll walk, and we have an example, but here's the formula. And we're going to calculate this probability and look at the table to find out what the power is. So the formulas could have been used to do the earlier power and sample calculations for the hypothetical blood pressure study that's in the text. To calculate the sample size needed for 80% power in detecting a change of 3 whatever that is. So alpha is equal to 0.05. That'd be we're wanting to have an alpha of 0.05. 1 minus beta is equal to 80%. Our delta is 3, and our difference here, so difference between 1 and 2, no, not our differences. This is our standard deviation. Our standard deviation is assumed equal in this case. There's a different formula for not being the same, and it's 12. So this formula yields a sample size of n per group. So we need a sample of, and we plug in those numbers into the formula that I showed you earlier, and we end up with 250.88, and we round that up to 251. Okay. Let's do that. Then we can use the power test. This is the formula that we found earlier. We can calculate that to find the probability that z is less than 1.25. And that, if you look at a table or you look at it online, it's 0.85. Okay, so now we have, and that turns out to be a little more than the 0.8 we were looking for because of the rounding, the 251. Okay, so we have formulas for power and sample size. We have another way of testing for mean differences. You know how we were only comparing against the two, well, for the feed, we only had the two different treatments. There's more than 2 treatments in the world. Okay. So if you were trying to compare multiple things, many different means, then we could use what's known as analysis of variance, or ANOVA. And you could conduct a bunch of different t-tests. Conducting the multiple tests on the same data increases the overall rate of type 1 error, and it's not good. So you don't want to do that. So what we do is we look for ANOVA using a single hypothesis to assess whether means across many groups are equal. So H naught, the mean outcome is the same across groups. Basically all the means are equal. HA is that at least one mean is different from the others. So i.e. not all means are equal. Now what on earth are we going to do? We're going to run this calculation, and we will be able to either fail to reject or reject the null, just like earlier with the t-test. But what does that tell you? At least one of them is different. Which one? That's when we have to go back to the old pairwise testing method to find out which one's different. But first you do the ANOVA to see if any of them are different before you go down that road. And the overall idea behind this, and we're not actually going to calculate one, is that we're going to compare the variability between groups. So how different are the group means from each other? And variability within groups. So how variable are the data within each group? So if you're comparing a lot of different feed treatments, you would be comparing the difference between each of the means of each of the groups, and that's the MSG, and the variability within the groups, that's the MSE. It's hard to know if 1, 2, or 3 are different, isn't it? If you're looking at that, like means, the means could be the same. It's hard to tell, and the same with this one. But it's difficult to discern in something like this, especially differences in means, because the variability within the group is, it's stretched across the entire space of the outcome, basically. Now these, I still think it's difficult to discern, but it's be more easily discernible because you probably have a mean somewhere in here for 4, probably somewhere in here for 5, and somewhere in here for 6. Now, whether or not that's actually different, that's hard to know. But the key is that there's the difference within the groups only spans from here to here, and here to here, and here to here, while the difference in means probably be less than that. It's just hard to tell. So we do a test. So under the null hypothesis, there's no real difference between the groups. Thus, any observed variation in groups is just due to chance. So you can think of all the observations as belonging to a single group, and variability within the group means that you should have equal variability within each of the groups. So we use what's known as an F statistic. And we calculate that by calculating this ratio. When all the population means are equal, the F statistic is approximately 1, but when they're different, the F will be larger than 1. And larger values of F represent stronger evidence against the null. This is a distribution that has 2 different degrees of freedoms. So DF1 is number of groups minus 1, and the DF2 is the number of observations minus the number of groups. And the p-value is p-value for F statistic is the probability that F is larger than the F statistic. So it's only in the F distribution is only in positive space, so you can think of it almost as the normal cut in half and folded over. We do have some assumptions we need to check for. Was whether or not conducting an ANOVA is appropriate. Our observations within and across groups, are they independent? So is it possible that one individual and another individual could be linked, or that their performance would be related somehow, or even within? So it's just important that each individual is independent. I guess the data within each group are nearly normal. we would want one of the things you can do is look at the data graphically with a histogram or a QQ plot. And we'll show you a couple of those here in a little bit so that you can know what that looks like. And that the variability across groups is about equal. Again, you can graph it. You want the variance to be rule of thumb, smallest, the ratio of the largest variance and smallest variance being less than 3 is about equal. All right. Normal QQ plots. So this is a probability. These are all probability density functions. The probability density function describes the line here, but they're basically just histograms where we're looking at where the observations fall. And in each of these, you can see different plots. So the QQ plot is not something I don't do it by hand. Let's see here. But what you're looking for here is for this diagonal line to have basically all the dots on it or near it. Because these are all roughly normal. This would be less so. This is definitely, I mean, doggone close. But you see here that also the impact of having larger samples. This is N of 400. This is N of 100. This is N of 40. So larger sample from a normal curve will result in that. If you end up with something like this, you have a problem. This is not normal, because you're deviating off of it, especially in these tails. That's what you need to look for. If the F-test indicates there's sufficient evidence that the group means are not equal, then you proceed with the pairwise. So your pairwise, you do a whole bunch of t-tests basically. And then to maintain your type 1 error rate at alpha, each comparison has to be adjusted to an adjusted confidence level that we call alpha star. There's more than one method, but there's this Bonferroni. Any ideas? I'm betting he's Italian, Latin, something. One of those corrections is, this is a method where we could correct. So it's alpha divided by k, where k is equal to k times k minus 1 divided by 2. So basically, we're just adjusting our alpha that we're willing to accept or that we're interested in. So, just a second. Okay, we have an example here. Again, we're going to use software here. We'll have to come back and do by hand with the homework and with in class on Thursday and Tuesday. Our main question of interest in that muscle response survey, though, was, is change in non-dominant arm strength after resistance training associated with genotype? So they had 3 different genotypes. So they wanted to know if they were any different, the responses were any different. And since there's 3, you're not doing pairwise at least not a first. So at least one group has our null hypothesis is that the mean percent change in non-dominant arm strength is equal across the three genotypes. The alternative hypothesis is that at least one group has a mean percent change in non-dominant arm strength that is different from other groups. Okay. And again, we'll have to do this by hand later, but you can calculate it and you end up with an F statistic of, in this case, 3.21 or 231. If you recall, one was no difference. But what we have here is a p-value of 0.0402, which is less than our alpha of 0.05. So we would say that we have sufficient evidence to reject H naught in favor of H alpha, HI. At least one of the groups has a different mean from the other groups by genotype. But again, now we don't know. Now we need to know which one has the difference. So now we have to do them all in pairwise t-tests. This will be referred to as post hoc testing. So we need to adjust like I was talking about and use this Boniferric correction. In this case, our alpha is no longer 0.05, it is 0.0167. Where is that on the table? It's not. So now we're entering a world where you need to have software. I guess we could maybe, software is needed, really. And unfortunately, it's trivial to do this with software because you see how we're able to compare all three of these with one line of code and we're able to find, here we have the pairwise t-test with pooled. So these are t's. Those the p's. Those are the p-values. So we have our p-values. Okay, there's no difference between CT and CC. There looks to be a difference between TT and CC based off of an alpha of 0.05. And there's no difference between CT and TT. See how you read that? CT and CC, you can test that. TT and CC. And CT and TT. So where we would have had to have done a bunch of different t-tests, the software is able to do it in a pretty slick fashion, just like that. Now this had no p-value adjustment method, and this one has the Boniferri, and it just ends up being, so they can be compared to the original. This software setup basically adjusts it so that we don't have to think about whether or not that we don't have to adjust our threshold. It adjusts the p-value that it comes up with so that we can still compare it to our alpha level of 0.05. So it's still that TT and CC are different but the others are not. Now, turns out that if your type 1 error for a single test is controlled basically by rejecting it only when the p-value of the test is smaller than alpha. And we keep alpha low, and within a two-group comparison at alpha equals 0.05, there's a 5% chance of incorrectly identifying an association where none actually exists. But what happens when you do a whole bunch of that? Because remember, you have alpha, or you have error potential in each of those tests, and that error compounds. So what happens when you make several? Well, their alpha is still used for each of the individual tests, but as far as the experiment-wise error rate, is the chance that at least one test will incorrectly reject H0 when all tested null hypotheses are true. So controlling for the experiment-wise error is one of the things we can do to control for that. This might look familiar from week 2. So the probability of experiment-wise error. So we're doing an experiment using t-tests to examine the possible association of two genes with a disease type. Assume the tests are independent and each are conducted at the alpha equals 0.05 significance level. Let A be the event of making a type 1 error on the first test. Let B be the event of making a type 1 error on a second test, where probability of A is equal to the probability of B is equal to 0.05. Basically, this is what we've been talking about of t-test experiment. The probability of making a type 1 error is equal across the test, individual tests, and it's 0.05. The probability of making at least one error, though, is the complement of the event that a type 1 error is not made. So this is we have a multiplication rule here. And we're looking for the complement of that. So 1 minus the complement of the probability of alpha, or the probability of the complement of alpha, and times the probability of the complement of B, which equals 1 minus 0.05 squared. So in here, so each of these were the same. The complement of the probability of alpha is 1 minus 0.05. So we're going to multiply them, the complement of A times the complement of B. And so we're squaring it there. And overall, we're 1 minus this complement. So our probability of making at least one error is 0.0975. So basically, there's a 10% chance of making one type 1 error, or at least one type 1 error. So the experiment-wise error is 10%, even though on any individual test, the probability was 5%. So it compounds on you. With 10 tests, you end up with almost just a little over 40%. With 25 tests, you end up with a little over 72%. With 100 tests, you end up with basically 99% probability that you'll make at least one type 1 error. But that's 100 pairwise tests. I mean, that would be a lot of things to test, but there's a pretty good chance you make at least one error.